Are you seeing the...
Okay, so we can start our seminar, today's seminar. So it's my pleasure to introduce today's speaker. Unfortunately, it's interesting that I never met Andreas in person, but we attended one of online conferences where he gave really very interesting and exciting talk. And so it was just motivation to invite him to give talk for our seminar. Just briefly about Andreas. So he got his PhD at the University of Oxford in mathematics, and after that he had a couple positions in, for example, in Imperial College London, and then in Columbia University, and now he is London School of Economics. Andreas works on several areas related to stochastic differential equations, in particular Makin-Vlasov equations, and also the applications to epidemiology and financial applications. Andreas, you are very welcome.
Thank you very much for the kind invitation and introduction. Very happy to be giving the talk in your seminar. Unfortunately, not in real life, but at least online. So last Christmas I had the pleasure of visiting Sydney Australia for the first time in my life, but I didn't make it down to Victoria or Melbourne or that area, so that will have to wait for another time. But I very much enjoyed my time in Australia, so hoping that I will have a chance to come back. It's a very, very exciting country, and clearly lots of good universities, good mathematics there. So I'm very happy to give this talk. So what I would like to talk about today, by the way, let me check, you can hear me clearly, right? Or
Yes, everything is fine.
Good. So what I would like to talk about today is a new thing I have been working on. In fact, it's the first time that I give a talk about it, so hopefully it will go okay. The title is Particle Systems with Moving Boundaries. And the sort of curious feature is that they're then governed by singular forward-backward interactions. This is joint work with Philip Jettkant here, who is at Imperial. Philip is a postdoc there in his second year, and so sort of looking for lectureships at the moment. I had been thinking about this problem for quite some time, and then maybe 1.5 years ago, I started working on it much more intensively with Philip, and the project is more or less done now. So we're hoping that by the end of the month, at least, there should be an archive preprint, but there is nothing quite yet, but soon it should be there. So if you find this interesting, please let me know, and I'm happy to share the preprint. So let me start first by talking about some different particle systems with moving boundaries that are considered in the literatures, and some that I have also worked on, and some that are related in some sense to the work today. The work today could be seen as a sort of a generalization of these type of things. So a classical idea is to consider n Brownian particles that evolve sort of advancing upwards in towards the Brownian particles as particles hit the boundary, and the boundary is then absorbed and grows further. So this is basically a sort of a version of what people call sometimes diffusion limited aggregation. So you could think of this lower boundary as some aggregate that is growing up as Brownian particles attach to it. And this type of system has been studied in several work. For example, Chase and Swintle here back in 1996 studied it and was interested in the convergence to Stefan problems in the limit. And sort of related versions of this were then picked up by my old supervisor, Ben Hamley, a collaborator, and myself, and also some people working in the US around the same time on this type of problem. I should say that many of these works are less about the particle system itself and more about what happens as you send n to infinity, whereas the talk today will really be about particle system. But just to explain what's going on in this kind of particle system, because it nicely motivates also what I will do later. The idea is that you have, for example, here 5 Brownian motions that start at some position. They evolve randomly in time, and there is also a boundary that is just flat because nothing has happened. then there is a first particle here that gets absorbed. So we cross it out, and when it is absorbed, it causes the boundary to grow upwards by some amount. Then the system evolves forward until the next time there is an absorption. In this case, there is another absorption, and now this particle here also gets absorbed. So the boundary would move by even further into the system, and so forth. Continuing in this way, leading to this red increasing lower boundary. That is, of course, making it more and more likely for further particles to be absorbed and for this boundary to grow even more. And so what people have been interested in with this problem is to relate it to something called the supercooled Stefan problem in the limit. So the supercooling basically is related to this fact that there is this kind of self-exciting or positive feedback feature that this boundary can kind of grow at a very fast rate. But okay, so this type of particle system is good to keep in mind, because in some sense the thing I will consider is a more complicated version of this. I also want to mention lots of work on different systems with a continuously differentiable lower boundary that is pushed away from the system instead of growing into the system. Rather than growing according to absorptions, you might consider reflecting Brownian motions, and you may then say that they are pushed according to their local times. So this has been studied, for example, by Frank Knight and later by Barnes here. So Knight studied the case of one particle and one barrier, and Barnes studied the particle system and also looked at scaling limits as n goes to infinity. So anyways, in my system, we will also consider n particles, and I will let them perform independent Brownian motion. But now, instead of having one moving boundary, each particle will have its own moving boundary. And similarly to before, a particle is absorbed if it hits the boundary. Unlike before, I'm not just looking at all times, I'm looking at some fixed interval of time, 0 to capital T, and we're interested in whether or not particles get absorbed before this final time, capital T. And so the idea is that it's sort of at any given time T, of course, depending on whether or not a particle moves up or down, it becomes more or less likely that it will hit its boundary. And the idea is now that it is this fact that whether or not it becomes more or less likely that you hit the boundary, that's what drives the boundary. So the boundary reacts to sort of the likelihood of hitting it rather than whether or not you have hit it, which was the case before. So before, in the system I showed you, the system only reacts once a particle hits, the boundary moves. Here, the boundaries will move in according to how likely it is that it's going to be hit in the future, basically, before the terminal time. This will become very clear later. So now, in order to describe how this goes on and how things are interacting, we fix some weighted adjacency matrix D, which is meant to be just a bunch of non-negative entries that describe how much each particle affects each other, so the strength of the interactions. And now we're going to say that at the final time, capital T here, we want the ith moving boundary to equal exactly the sum of these dji's, so how much j's absorption impacts particle I, and we sum over all the particles that have been absorbed. So at the terminal time, this is exactly like in the previous system that I showed you. At the terminal time, capital T, the boundaries will just have, if we take these dji to be some given fixed constant, all of them the same, then this is the same sort of outcome as in the previous system, right? We're just saying that if I stand at the final time, all I need to look at is exactly how many particles were absorbed, and according to how many were absorbed, the boundary will have moved by some amount. So now the interesting bit then is that what we add on top of this. So of course we could now say that at any time little t, the ith moving boundary should just equal the same sum, but only with the set of particles that have been absorbed up until time little t. And if we do that, we would basically get back to the previous particle system. But what I'm going to do instead is I'm going to say that at anytime little t, we want the boundaries to not only reflect the realized impact, so how many DJIs have already moved the boundary, we also want it to reflect the expected future impact based on the available information, which we take to mean that it should be a martingale in the full Brownian filtration of the system. So basically, we're looking for moving boundaries that satisfy that they have grown by this at the terminal time capital T, and that they were martingales for the set of n Brownian motions that are driving the particle dynamics. And so to give you an idea of what this sort of system could look like, here's imagine a discretized version of the system. We take just n equal to particles. We start them at the position 1, so they start here, and we take the adjacency matrix to be the identity. So that means that upon the absorption of the first particle, the other particle feels an impact of 1, and vice versa, right? So they each feel an impact of 1 upon the other's absorption. In particular, we know that at the final time capital T, there can be 3 situations, right? Both of them could be at 0. One could be at 0 and one could be at 1, as we have here, or they could have been up here at 2 if they had both been absorbed. In this case, what have happened is that the boundary of the purple particle is at 1, which reflects the fact that the orange particle was absorbed, because the fact that, and as you see here, the orange particle was absorbed at this time here, because it went below its boundary. And the fact that the orange particle was absorbed immediately meant that the boundary of the other particle is now at 1, and it stays at 1. It has had the full realized impact. On the other hand, the purple particle here is never absorbed because it always stays above its corresponding boundary. So the dotted lines here are the Brownian particles, and the full lines are the moving boundaries. So the purple particle here stays above its moving boundary. So it is not absorbed, and therefore in the end, indeed, we have that the moving boundary of the other particle is not impacted by this at all. It ends up at 0. Of course, what is interesting here is that along the way there was indeed an impact, right? And so if we try to see what goes on, we can see that, for example, here at the beginning, the orange particle goes down, making it more likely that it will become absorbed, but at the same time, the boundaries actually go down. And the reason they go down is because, well, the purple particle went up. And the fact that the purple particle went up, that meant that it's less likely that it will be absorbed. And since it's now less likely that it will be absorbed, it pushes the orange boundary down. And since the orange boundary has pushed down, the fact that the orange particle went down is not a problem. In fact, it's less likely to be absorbed because the boundary moved down by more. And so also the purple boundary, which is driven by the orange particle, also ends up going down. Then at the next step, you can see both particles go down. This makes it definitely more likely that we will see absorption. And so both boundaries are picking this up and moving up. Then the purple particle goes up. So now things go back down again, and it looks more safe. But then the orange particle keeps going down, and also the purple particle goes down. That causes really a spike in the boundary of the orange, enough to drive the particle position below the boundary, meaning that the particle has now been absorbed. And indeed, the purple boundary has now moved to 1. So hopefully this makes at least a little bit of sense. I just want to try to sort of motivate the dynamics before I write down a more precise problem. So now, just to give, by the way, if there are any questions, please feel free to interrupt. So here's another illustration with 3 particles, just to see what could happen then. So in this case, we take just the adjacency matrix to be 1/2, 1/2, 1/2 along along the diagonal, meaning that they each impact each other by 1/2 upon a default. So this means that we can end up either at 1/2 or 1 or 1.5. If we end up at 1.5, then it would be because all 3 particles have been absorbed, and all 3 boundaries would be sitting here at 1.5. Instead, what has happened at the terminal time is that two particles have been absorbed. So the purple and the orange have been absorbed. That has caused the green particle here, or the light blue particle, to be at 1 because it has felt 2 absorptions, and the other has felt 1 each, so it is at 1/2. And you can see the similar sort of behavior from before. At first, everything is quite far from the boundary, so the boundaries are almost just the same, and they're quite low. They're moving a bit up and down, depending on the up and down movements of the particles. And then here towards the end, something starts to happen because all of a sudden it becomes very likely that these two particles are going to be absorbed. The fact that it's very likely that they are being absorbed is driving up a lot the boundary of the green particle here. So anyways, as you can see, it's a similar sort of system as the first one. But of course, now the boundaries are no longer just increasing processes like they were before. They are martingales. And also we have this sort of complicated interaction over time. We cannot just fix one given time and look at what's going on there. We need to sort of really look at what happened in the past and what could happen in the future. So to give one way to give a precise formulation of this problem is to realize that actually what we have written down is just some kind of version of a forward-backward stochastic differential equation. So we have the forward particles moving here, and then we have the moving boundaries, which will be specified by these indicator functions here, that these indicator terminal conditions that then have to move according to some stochastic integral against Brownian motion, right? So assuming that these spaces here, by the way, so these here too just mean we have sup control, and the H just means that there is some L2 control on set. Since there is some L2 control on set, this here is a true martingale, and so it's satisfying the sort of criterion that we have. And the idea is then that we can now define the particles we're interested in. So the particles are the xt up until the time that they're absorbed, and the moving boundaries are given here by the sum of these backward processes yj. So the absorption times are the first time that the particle I drops below this moving boundary here, which is this sum of these basically conditional probabilities yj multiplied by the impact that I has on j. So what we have is basically just a forward-backward system, but what is interesting and what has not really been treated before is the fact that, first of all, this thing is, of course, singular in the sense that it depends on an indicator function. And second of all, it's singular because it depends on these hitting times. So as we saw, for example, as I was sort of illustrating in these pictures here, of course, this means that the backward process degenerates, right? The volatility goes to 0 and it just stays constant. So that's this set here can degenerate. And another way in which it is singular is, of course, that whenever one looks at hitting times, well, you can always have this phenomenon that two paths could be uniformly close to each other, but one has crossed the boundary and the other has not, and therefore the terminal condition is completely different. So that's the reason for the use of singular in the title of the talk. So the first thing one can realize is that there is actually a rather easy way of getting at least a solution to this system. But that easy way will not really tell us anything about properties of the solution, and it will not tell us anything about uniqueness and so on. But it's the way I came to the problem. It's the first way that I realized at least something could be done. And then as I've been working with Philip on this, we realized that one can really say a lot more. So the idea is to rely first on Tarski's fixed point theorem. And so I stress when I say an adjacency matrix, I mean a non-negative matrix in the sense that the boundaries are always impacted upwards by absorption. This creates a sort of monotonicity at the final time, in the sense that if we insist on a larger terminal condition, then using the martingale property, this leads to the whole backward path being higher. And if the whole backward path lies higher up, then that means that hitting times will happen earlier. And if hitting times happen earlier, then it means that this indicator function here is more likely to be 1. And this indicator function is meant to be this. So there is this kind of monotonicity property going on. Sorry, let me have a glass of water. And the fact that we have this monotonicity, one can make this precise and then apply a version of Tarski's fixed point theorem to argue that there must at least be minimal and maximal solutions to this problem, where minimal and maximal means almost surely pathwise in Y. So the minimal and maximal solutions are ordered in that way. So that at least tells us their existence, and there might be minimal and maximal solutions. Now, for the rest of the talk, I want to analyze the problem a bit further. And in order to not get too tied down in notation, I'm going to focus on the symmetric case. So by the same type of arguments, we can handle the asymmetric case. So this is purely to make the notation lighter. So what we're going to do is we set all the Dij's equal to some given positive alpha. So everything is affected in the same way. That helps us a little bit because then we can simply define one Y to be the sum of all the backward processes and one driver set to be the sum of all the drivers. And then we get this system of FBSDs here where we now just have one boundary down here. So we don't need to worry about n moving boundaries. And crucially, when we try to analyze the system, since everything is symmetric, we only care about how many particles are currently alive or how many are currently absorbed. We don't really care about which ones because they all affect the system in the same way. So we have made this a slight simplification here of the system. It's still basically as singular as before, but the notation becomes lighter. So when looking in the standard literature on FBSDs, the one thing that one always wants to look for is what's called the decoupling field, right? So for those of you, I mean, you don't really need to know anything about FBSDs to listen to this talk because we are not really able to use any existing theory from FBSDs. We have to do everything sort of tailored to the problem here. But the idea of so it doesn't really matter whether you know anything about when and how decoupling fields might exist. The key thing is just that the idea of a decoupling field is that one ought to be express the backward part as some function of the forward part. And if one can do that, then you have, of course, decoupled the system and gotten back some kind of Markovian system. If we take yt to be some function of xt, we can plug that in here, and we would now have that y is just some u of xt here. And then this is some nice Markovian system that is only determined by the forward processes. Now, if one stops and thinks about this for a minute, not even worrying about the singular aspect of the problem, it's clear that this cannot be true in our case, because if one only depends on the positions on the x, these are just the Brownian motions, then we have no information about which particles have currently been absorbed and which have not been absorbed. So we cannot have this kind of property, right? We would need to look for something slightly different than this. But what it turns out that we can do is that by tracking absorption, we can sort of, in some sense, unravel the decoupling field into n decoupling fields that correspond to some decoupling field Vk, where k is the number of particles that are remaining in the system, so that have not been absorbed. So we need a decoupling field for there is 1 remaining particles, there's 0 remaining particles, there's 2 remaining particles, there's n remaining particles. And then it will turn out that we can indeed express the forward part then as these decoupling fields evaluated at this other random process nt, where nt is tracking the number of unabsorbed particles. And this is where the symmetry assumption really helps us, right? Because here we only care about how many particles are currently absorbed. One could also write this down, for the general asymmetric case, but then we need a whole set of these functions that depend on which particular particles have been absorbed, whereas now we can just worry about the number of them, okay? So what we expect and hope is that we can find this kind of more generalized decoupling field that would somehow say that we do have some Markovianity, but only when we keep track of the x's and the absorbed particles. So the question then becomes, what sort of a PDE problem does one need to solve in order to find these V1 up to Vn? What are their domains? And what are their boundary conditions? So what we will realize is that their boundary conditions are actually tied to the system below it, because we know that the boundary has to do with when you reach the boundary, then one particle gets absorbed, and therefore there is one less particle in the system. But that brings us down to the system described by Vk minus 1. So we know that at the boundary, there must be some kind of correspondence between Vk and Vk minus 1. But whether this can work out and whether it can be done was something that, puzzled us for a long time. So what we do is we start by staring a little bit at the initial particle system, and we recall that particles are alive as long as xt is bigger than alpha yt. Now we have expressed yt as this kind of function here, which is just what we discussed before. So that basically tells us what the domain should look like. So the domains have to be something like, if I look at the smallest particle, so the smallest value of a remaining xi, when there are k of them remaining, then I look at the smallest of them, and the smallest of them needs to be bigger than alpha times the case decoupling field evaluated at the whole set of remaining particles. So, and what we then get inside this domain is that since the particles are just doing independent Brownian motion, we should get this k-dimensional heat equation here. This is nice because we know that the heat equation is very well behaved, but of course we could be a little bit worried about the strangeness of this domain, which involves a minimum and which even more strangely involves the solution to the PDE itself here. This, it will turn out, we can get rid of, and so we will be able to solve things nonetheless. I will show some pictures in a minute that hopefully also makes this more clear if it's a little bit full of notation at the moment. Now, suppose we consider a pair Tx, so a time and positions of k particles that are outside the domain dk, so that are not satisfying this. Well, in this case, we know that the particle, let's call it I0, with the minimal position, so must be absorbed. And so we are left with a system of size k minus 1. So this tells us basically that at the boundary, we must have the boundary condition that Vtk of x should equal the system one step down, where we project away the smallest particle. So that's what I'm saying here, right? Here I'm just saying remove I0, which is the particle that is currently has the lowest position. We project that away. The reason we can just focus on the lowest position is because everything is symmetric. So we know that the particle with the lowest position has to be the one that would have gone if it could go. If it and this then takes us actually one step further, because this is not only a boundary condition, but a moment's thought also reveals that we can actually use this in the definition of the domain. So basically, if the minimal particle I0 can be absorbed, then it will be absorbed. This is in some sense an assumption that we make, but it will turn out to give the right solution. If you go back to think about the fact that there might be maximal and minimal solutions to this problem, at least a priori, we're saying, let's focus on the maximal solution, where maximal solution means that we always absorb if we can absorb. And so that basically allows us to change the domain in a way where we say, well, if the minimum particle is bigger than alpha times the system where we project away the ith particle, meaning that we treat the ith particle as absorbed, well, then we absorb. Okay, so if there is a particle that could be absorbed. Sorry, if I mean, I'm talking about the being outside the domain here, so maybe it's easier if I say that, assuming that all the particles are bigger than the case where we move the boundary by the amount alpha, because we do absorb the I0 particles, so we have moved things as far as we can. And if everybody is still safe, well, then it means that the particles should indeed stay alive, and so we can take this to be the domain. Okay, so this is absolutely crucial for things to work, because it would be very complicated to try to solve this PDE together with having itself in the boundary condition. Sorry, in the boundary of the domain. But what we now realize is that we can actually take the solution to the system one step down and use that in the domain, which suggests that we might be able to do something inductive here in order to deal with this system. Okay, so if we know if we can solve the system with everybody absorbed, then we can use that as the boundary for the system with one particle remaining, and so on and so forth. Of course, everything is still linked to each other, so it's still a free boundary problem, but this drastically simplifies the situation. So what we have obtained now is what we call sort of a cascade of free boundary problems, because it unravels as this cascade between 1 to n particles having been absorbed. We have the heat equation inside these domains that we described. Outside the domains, we have to agree with the system below when projecting away the minimal particle. So of course, slightly complicated function that sits in here because it projects away the smallest particle. And then we know that at the terminal time, if we have made it to the terminal time and we're inside the domain, well, then nothing was absorbed. And so since there were k particles remaining, we now just have that there is n minus k particles absorbed. There were no further absorptions. Remember, there were n particles initially, k of them remains. That means that n minus k have been absorbed. What we can say immediately is that if we were to look at this kind of system in the zeros case, then we just have an n here, right? Because in the zeros case, nothing is going on. It's just everything has been absorbed. And so there's just always n is the value of the boundaries, basically. So alpha times n is the value of the boundaries, but this here is capturing the indicator functions between 0 and 1. And we have these domains here, which is just what I described before. So now the goals of our project is then, now that we have managed to derive some kind of free boundary problem that describes our thing, well, can we at least establish well-posedness of this? Can we use it to basically verify that there is a solution to the FBSD, which is given by this free boundary problem? And can we also finally establish uniqueness of the FBSD? So in the talk today, I will not really talk too much about the proofs. I more wanted to really emphasize here how we get to the problem, what the problem looks like, and so on. And I will just give you a few results and a few ideas about how we prove it, but not too many details. So let's consider the simplest case in order to get some understanding. So let's suppose we have a system of just 2 particles, and there's only 1 particle remaining. Now, we know that if there were 0 particles remaining, then we just have 2, because they have, with 0 particles remaining, 2 of them have been absorbed. So that means that the domain for the system with 1 remaining is given by just plugging in here alpha VT0. Sorry, this should have been a 0 up here. That's a typo. This here should be this. Then we just have alpha 2. So the domain is just 0 to t times 2 alpha infinity. So we're just on a half line. We're no longer on a moving boundary. That means we're just solving a heat equation on a half line with a boundary condition, and we can do that with a boundary condition directly corresponding to absorption. So we can do this, and we have an explicit solution which looks like this. So this was kind of actually a little bit surprising to us at first, that there was going to be some explicit solution hiding somewhere. Now, as we go further down the cascade, we're not expecting to have explicit solutions anymore, but at least there is then a version of the system, the simplest case, where we have an explicit solution. And let's try to plot it for alpha equal to 1 here, so you can see sort of what it looks like. So if we look just to start with the terminal time, so terminal time is 1 in this case. In the terminal time, since alpha is 1, we see that, well, if the particles are anywhere below the value 2, then the boundaries will already have moved by 1 because there was 1 defaulted, and they will move by 1 more if the second one defaults. So we'll look anything below 2 is killable by this move of 2, and therefore would result in the total number of absorbed particles being 2. On the other hand, if at the terminal time a particle is bigger than 2, well, then the 1 from the already absorbed particle and the 1 from its own absorption is not enough to kill it. So this part, all the particles sitting on this line are not absorbed. So either they're not absorbed or they're absorbed if they have this position. And correspondingly, the final outcome is 2 particles absorbed or just 1 particle absorbed. So this is sitting at 1 because there was already 1 particle absorbed, right? There was k equal 1 remaining. On the other hand, at earlier times, of course, it is possible for a particle sitting, for example, at 2.5 to be absorbed. And this here describes the probability. And this is simply reflecting the fact that there is some probability that the Brownian motion goes down and crashes into the fixed boundary here. As time goes on, these probabilities become smaller and smaller. And the singularity of the problem becomes evident here, right? Because this then has to go down and equal this let's say, Heaviside function here. So now let's use this to move on to n equal 2 particles with 2 particles remaining. So this is where we're really using this inductive cascade property, because now we know that we have V1, which we just solved before. So now in our domain, where we need to look whether the minimum of the particles is bigger than alpha times the maximum particle evaluated at the solution 1 step down, we can just plug in the explicit solution. And since we then at least have an explicit expression for the boundary, and in this case just the 2-dimensional heat equation, we can solve this numerically. Going beyond this, it's very tough to solve this problem numerically, and so indeed this is something we're looking a bit at as well, the ideas for doing this. But let's do a plot here with alpha equal 1 as before. And so before I run the simulation, let me just give some motivation here and note that, for example, if x1 is below 2, and if also x2 is below 2, so we're in this region here, then both of them defaulting would, sorry, I say default because I will talk about finance later. So both of them being absorbed would mean that the boundary moves by 2, and so is enough to absorb them. So anything in this rectangle here would always be absorbed. If we are right here, so x1 is equal to 1, and x2 is above 2, then on this line here, exactly one of them would be absorbed. And similar here, so along this line, the solution would be 1. Oh, now I'm running it. So here the solution is 1, here the solution is 1. As it's possible to be absorbed here, but as time goes on, the things that are in here, it's no longer possible to be absorbed. And so at the final time, either you're in the square and there are 2 absorbed, or you're out here and there was nothing absorbed. So hopefully this makes a little bit of sense. 1 second. As I was saying here at the end, note that the boundary has a kink here. So this there is some irregularity here, which kind of stops you from applying standard regularity results in dealing with this system of PDEs. But yeah, so just to stress again, right, if the particle x1 is sitting here at 1, and the other one is up here, then the x2 particle, which is above 2, will not be absorbed, but the x1 could be absorbed. So here we're looking at the value 1. We're looking at the value 1. We're looking at the value 2 because both are absorbed. And then we're looking at some interpolation of those values, where right now particles in here at time 0 would be below the boundary of and be absorbed because it was so likely basically that they could be absorbed, whereas things out here is very unlikely that would be absorbed, and so it's basically 0. So for the well-posedness of this, it turns out that with a suitable description of a classical solution, we can indeed prove that there exists a classical solution, and there is even a unique such thing to this system. So a classical solution means that you should at least be continuous up to the boundary, and the C12 in the interior, of course, satisfy the equation, and there should be some regularity as we move towards the terminal time. So let's not worry more about that. So there exists a unique classical solution, and we can unfortunately not appeal to any really existing results because of these boundaries. We don't have a good handle of their regularity. Even the boundary in the one-dimensional setting that we just saw here, so the red line, is irregular. And once we move further on from that, we have very little control over the regularity of the boundaries. But it turns out that we can sort of basically do the thing by construction. So the idea is, again, to work iteratively. So it's really always these kind of inductive arguments. We define what we think should be a solution, and then we verify that this is indeed a solution. And some tricks that come down to really just particulars of the system allow you to then also deduce the regularity. So the idea is simply that you run some Brownian motions, you project away the minimal state, as we know we need to do, and then we just evaluate at the time where the boundary first hits where the Brownian motion first hits the boundary. If it does this before time capital T, if it does not hit the boundary, the Brownian motion before time capital T, then we just set it to be n minus k because no further particles were absorbed. So we take this as a definition and then show that indeed it leads to a solution. And then there's a separate argument, basically sort of based on a contradiction type argument to show that there is uniqueness. So now this I will just go over very fast and say that we can also have a verification theorem. So we can link this unique classical solution to the unique classical solution to the PDE can be linked to the FBSD system. The idea is to use the PDE and construct it iteratively and then paste all the solutions together. So basically, you can start by looking at the case where there are n particles. Then you define what the y should be, like with an n up here. Then you run the system until there is some absorption according to this rule. Then you look at the system with one less particle, and then you define appropriate stopping times and paste everything together so that it behaves according to one system until the first stopping time. It behaves according to the next system until the next stopping time, and so on. And it turns out that then you get this equality here, and you indeed have that you satisfy the FBSD as desired. So we call this a verification theorem because we're just verifying that this kind of free boundary problem that we postulated should be true is indeed true. It does give you a solution to the particle system that we were interested in. The next thing we can do is then establish a pathwise uniqueness for the FBSD. So as I was saying before, the uniqueness doesn't really seem to be deducible by estimates, but what it turns out is possible is to rely on a sort of a contradiction argument, basically. And the idea to sort of keep in mind is that one first gets a handle on what the solution should look like from the PDE problem here, right? And then you show that this has to be the unique solution. If there was another one, it would end up being that. In the one-dimensional case, there is quite a nice little proof that one can do, which is basically sort of using the fact that the particles have to be absorbed as soon as they can. If there was another solution, then assuming that that solution leads to particles being absorbed later on leads to a contradiction when you look at some probabilities involved, basically because if the particles were to be absorbed a little bit later, the system would actually already have anticipated this, and so it would have happened earlier on. It gets a little bit involved, but that's the idea. Happy to answer any questions if there are questions on the details. I would rather now just end the talk on a lighter note by going back to one possible application of this kind of system. So one thing we can do is consider a topic of contagion in financial networks, which is something I have worked on quite a bit in the past. A very typical setting in the economics literature is to consider some financial network that is described, let's say, by some banks that each have some exposures to each other. For simplicity, let's just call them debts, but it could be more complicated contracts. And we make the assumption that we are today at time 0, and all these things are due in the future at some time capital T. We then say that the financial network is described as follows. So there are some outside assets which are independent for each institution, and they're just doing Brownian motion. Then there is some interbank assets, which is because, so let me make sure that I wrote these correctly. So anyway, so let's just assume here that, yeah, these are interbank assets because, one second. So we are due to be paid some money. So I guess I should maybe have written J to I, but it doesn't really matter. So the interbank assets here just means that J will pay I this amount, and on the other hand, I will also pay J some amount, so we also owe some amounts away. So these here are amounts that we are owed by others that we will collect at time capital T. These here are amounts that we have to pay at time capital T. And then there are some outside liabilities that have nothing to do with the system. And if you just study a static system, well, then the capital of each bank is just the sum of the asset minus the sum of the liabilities. Now, what one could do, and something that people are interested in the economics literature, is to say that what if there is some sort of information contagion within the network about the solvency state or the health of these banks? And one way that this is captured is by enforcing mark-to-market valuation, where we say that, well, these DIJs here that I expect to get in the future, well, in fact, I might not get them if the counterparty is in default or has been absorbed. And if we assume that there's zero recovery upon default so that I get nothing, then really the mark-to-market values, when we account for this default risk, are given by scaling down the initial assets to the initial assets multiplied by the conditional probability that the counterparty has not defaulted and therefore is able to make the payment. And of course, we can rewrite this as 1 minus the probability that it has defaulted or has been absorbed. This then leads to the following problem, where by rewriting things, the capital, once we change these DIJs to these scaled DIJs, and we rewrite according to this, then what we have is that the capital of each bank is now negatively affected by the probabilities that the other banks might not survive until the end. So based on all the information that's available today, the system is affected by the expectations about whether or not the person here will be able to make the payment or not at the final time. And we declare that an institution is in default if this capital reaches 0 at any given point in time. Now, if we take this filtration FT to be the Brownian filtration, then treating this here as the particles and treating this here as the boundary, this is exactly equivalent to the FBSD problem that we have discussed in the talk. And so with that, I just want to finish with highlighting a few future directions that we're interested in. So first of all, while the particle system here turned out to be quite difficult to analyze on its own, in the symmetric case, it's natural to ask what happens as the number of particles tends to infinity. Can we get something meaningful that is simple to analyze and which simplifies the system? Because the system is rather involved to compute, so having a simplified mean field limit could really make the analysis of the problem easier. But it's not immediately obvious because since we lack a bit of control on the system, it's not so easy to get a tightness for this kind of thing. So this is a completely open problem. We have some conjectures on what the mean field limit should be, but actually proving that is a completely open problem for us. Now, a second thing that could be very interesting is to do either a finer analysis of the PDE or some estimates relating to the FBSD in order to be able to say something precise about the backward volatility set. This would be interesting because one could make some conjectures about the fact that if we look at the FBSD system, one would sort of expect this thing to go crazy when the particle X is close to the boundary. So you would expect to see a lot of excess volatility when you're close to the boundary and less volatility when you're away from the boundary. You would also suspect that there should be some sort of relation that when X moves up, it should not change set so much if X was already far away from the boundary, whereas if X was close to the boundary, a move up would change things by a lot. Similarly, if you're far away from the boundary in general, similarly, you would expect in general that moves up away from the boundaries affect things by less than moving down. So basically, what is the volatility of these martingales as you're close to the boundary or far away from the boundary? Since we know that they can be expressed here through the PDEs. Of course, we also know that the set is related to the derivative of this thing in a suitable way. So if one had some knowledge of the derivative of this function, one might be able to say something quantitatively about how the derivative of V depends on where X is and how that therefore affects the volatility of the system. Next, in the financial setting, there is this an obvious extension, which is to say, of course, the world does not only involve a final time capital T, so one could have multiple maturities T1, T2, T3. And then a slightly easier question is to simply extend this to more general coefficients and, for example, correlated Brownian motion. So for this final point, we suspect that the same approach that we have taken here should work, assuming, of course, some regularity on the coefficients, but we haven't worked out the details. Also, the multiple maturity setting should be doable, while the two first problems really, I think, are quite significant directions for future work. So with that, let me stop here and thank you very much for listening.
Thank you very much, Andrea. Perfect on time. So just if you have any questions, please unmute yourself and ask.
Very happy to also just explain figures or anything in more detail if the equations are boring.
I have probably a quite naive question. So you considered probably related to your financial applications. You considered Brownian motions, the collections of Brownian motions. But if you move to other types of processes, like more advanced, like fractional Brownian motion or even more, do you think that it's like doable or it's too complex?
So wait, let me see. So I mean, of course, one could certainly formulate the problem, right? So one thing that I would say is that at the moment, if you want to at least take the approach that, so what we found is that it's very hard to analyze the system of forward-backward equations themselves. So almost all of our results rely on the PDE approach to this problem. We get very, very little, only this Tarski fixed point problem, which you could definitely still do for more complicated processes. So I think that the having existence of a minimal and maximal solution could work in a lot of generality for the processes instead of Brownian motion. But when we get to solving these systems here, I mean, we really rely on having these classical solutions with that are continuous up to the boundary and which are differentiable in order to apply some Ito formula to connect them back to the particle system. So I guess that wouldn't be so clear to me, right? I mean, there would be something different to do there. So, but if you can analyze the corresponding PDE systems, then I guess something could be done. And one thing that would at least be positive is that we take this slightly constructive approach. You just try to write down what you think the solution should be. And you could, of course, try to do something similar maybe for more general processes. But what I would not know is whether you would succeed in verifying that that this thing satisfies the right thing and has the regularity properties that you need. This I would worry about. But for sure, for example, the fact that there exists a solution through this TASCII fixed point, this I think would work in complete generality.
Something.
At least in the right way, because to be honest, we do use the martingale property there a little bit, but I think if you set up the spaces in a slightly more complicated way, you could do it pathwise for some processes in a slightly different way.
Okay, thank you. Another just maybe clarification. You mentioned that when you move to case with more than 2 particles, so you can't like even numerically to show anything.
Yeah.
Yeah. Does it mean that you can't simulate like using some like simulation methods? You can not just numerical mathematics, but just simulating a lot of particles and just to get in these things.
It's very complicated because of this this forward backward thing, right? You need to do so many iterations because you need to solve everything, and then one thing you can basically do, sort of a naive way to do it, is to start by assuming that the boundaries are all at 0; they have not moved at all. Then you can simulate a bunch of particles. You can see where they end up at the terminal time. You can count how many were absorbed or not. You can use that to update where you think the boundary should be, and you can continue doing this. But it's very, very expensive to do. And it's only really easy to do in the first iteration. In the second iteration, you need to do these kind of complicated procedures. So yeah, it's really one thing we're exploring a bit now is whether you can do some neural network type of stuff. So, there is these deep BSDE methods, which maybe people have heard about, just to get an understanding, because it really seems like it's very tricky to simulate. So I would say 3 particles with some symmetry assumptions, it can probably be done. You can also have some connections that are a bit acyclical, that sort of breaks up into subsets and stuff. But yeah, I think if you wanted to solve this system for 4 particles, for example, you would run into a lot of problems.
Okay, I see. Okay, thank you. Any other questions or comments, please? Okay, if not, I think it's quite new and complex talk. So if somebody has questions, of course, they can contact Andreas, and just like paper will be published soon, so submitted to archive, so you can look at details. Okay, Andreas, thank you very much, especially for early morning in UK. So have a good day.
Thank you very much to you, and thank you very much for the opportunity to present it. As I said, it's new work, so we need to see how to present it in a good way, and it's definitely a little bit of a specialized topic.
Thank you. Bye.
Thank you. Bye bye.